Welcome back to Munro Live, everybody. Today we have the Lucid Air rear drive unit, and we have Walker with us. It's the first time you've been in a video. You've been at Munro & Associates for a couple years now, right? And you're one of our rising engineering stars. So we're going to run through what you found, a lot of the intricacies that we see on the table, and let's hop right in. So where are we going to start? We're going to start with maybe one of the planetary sets, or maybe the general layout.
Sure.
Maybe, let's do general layout.
Okay.
So we have a shaft over here, and I'll roll this way. And this is right in the center of the unit. And explain how the laminates for the rotor are sleeved on here. Explain where the little differential is. Actually, I'll grab that. So we have this tiny little differential in the center. Is that correct? And it interfaces with the center of the shaft with these small pins. There's 4 pins, and you can see how it slides in here. But in order to actually assemble it, we have this like loosely bolted together just to show how it works. But what's unique for the Lucid is that this is in the center. And oftentimes when there's a planetary set in an electric drive motor, they'll put the differential in the planetary set, and then they'll have a shaft that runs inside of here. They're not doing that. They're sending the power from the stator to the rotor. They're spinning the rotor. The pins spin the center of this, and if the wheels are moving in the same speed, this thing stays essentially locked. And as you go around a corner, one spins slightly faster than the other, and it rotates. And then it's going to interface with the sun gear of the planetary set right here.
Exactly, yeah. So they're placing their differential pre-gear reduction, which is one of the reasons that we see it so small here in front of us.
Now, why is that? The torque demands are a lot less because you're not seeing the torque at the wheels, you're seeing the torque at the motor before the gear reduction.
Exactly, yeah. They're running this at motor speed, not output speed. So this is seeing far less torque than it would after it goes through this planetary set, which is a 7-to-1 gear reduction. So the overall load that this sees is far less than that we would see on like a Tesla, which we could bring over here. Additionally, they have 4 pinion gears as opposed to just 2 that we would typically see.
Oh yeah, cool. And then we have one of the planetary sets kind of taken apart here. So you have the sun gear, and then you have 3 planets, and then they react to a ring gear. Is that correct?
Yes.
And then as the carrier spins, this would be wheel speed.
Exactly.
So the speed of the carrier is wheel speed. And one thing I noticed that was kind of different is the OD of the sealing surface and the bearing surface. And we have the seal actually installed on this one. Now, we were talking about this the other day. This is going to be a higher speed, right? So the further out you are, the higher the speed is. So it'd be kind of interesting to see if they have any service issues with this, you know, late in life. But typically you want these seals. This is a pretty standard design. It's what I see on like the slip yoke of a transfer case. I had a 2500 diesel truck in another life, and it was slightly smaller than this, but it was pretty much the exact same design. But what's really nice about this drive unit is that it's centered. So you have the motor in the middle, you have 2 identical planetary sets, one on each side. So this planetary set is only taking the power of half of the motor, right? So one of the wheels. And if you think of a Rivian, which has a quad motor, they'll have one motor driving. Do they have a planetary set or do they have an offset gear?
Rivian was using offset, I believe.
Offset, yeah. So they have one set of gear train handling all the power from one motor, and then they have another motor driving the other. It's really refined. And I know that Peter Rawlinson, they did that really nice video, and they talked about how dense this thing is. And it's so small, and it's quite amazing that they're able to get this much horsepower in this unit. So it's 669 horsepower.
Yeah, it's capable up to 669 horsepower. This particular vehicle had a front and rear drive unit, but yeah, a lot of people walked by this when it was coming apart, and I think that was the first thing everyone said was just looking at the size and knowing the performance characteristics of the vehicles, to see something this small was pretty impressive.
Yeah. Talk about the magnets. What did you see on the magnets?
Yeah, so the magnets themselves, so the rotor, you can see there has keyways, so this slots over the rotor shaft after the differential is installed. So they have 2 of these laminate stacks with magnets, and you can see that there's epoxy down the magnet slots to hold these in place. And these are actually segmented magnets. So some of the original Teslas utilized these segmented magnets, as opposed to they have since transitioned to just one-piece magnets. The segmented magnets, you have some efficiency benefits of not having the eddy current losses. So there might be some marginal efficiency benefits to doing this, but overall, it's a pretty simple rotor design. There's 2 of these laminate stacks that get slotted over the rotor shaft.
Yeah, right here, you can see the slot.
Then they used some die-cast end caps to cap off either end of these, and it's actually a pinned assembly. So due to kind of the nature of how this gets built up with the diff having to be installed first, they actually have this be able to be built up as a sub-assembly separate from the rotor shaft using those die-cast end caps we can bring over.
Yeah, what was our idea behind why the shaft itself had these broach marks? I mean, they look like little broach marks. Do you know why that is? Is that so that the electrical conductivity doesn't go down here? Why is that? Do you know?
We don't have any definitive reason. Overall, I think it's just going to help them have some retention on these. You can see this isn't a knurled surface per se, but overall, this spline fitting is definitely going to provide some additional securing of the rotor stack.
Okay. And the end caps, these are aluminum and they're common.
Yep.
Besides the drilling they do for balancing.
So after the entire thing is assembled with the differential in it, then they would do this additional machining afterwards to just ensure that the overall rotor assembly is perfectly balanced.
Yeah. And then here, for position of the rotor, you have a pretty standard, was this a resolver ring?
Yeah, yeah.
But the target ring is really kind of unique. It's integrated into the shaft.
Yeah, we've never seen anything quite like that.
Yeah. So based on the shape of this is how they're figuring out what position the rotor's in. It's kind of unique that it's not a separate part. If we walk over here, Eric, we'll actually show you what these target rings look like on a couple other motors. So we have a Rivian shaft right here, a Model S Plaid, sorry. The Model S Plaid. You see it's a similar shape. It's like this trilobal shape. And this target ring is made up of a stack of thin laminates. And then on the Rivian, you have this quad lobe on the end, much smaller. So from a material perspective, this is pretty small. And here's another example of one. Do you know what
that was off the Lightning.
Off the Lightning. So it's very common for them to use these stacked laminates. So seeing it integrated as a piece of as a part of the machining of the shaft, it really reduces part count, but not necessarily weight, because the Rivian with this little tiny target ring there, that's kind of probably your lowest weight.
Yeah.
Right there. And as that also drives the size of your resolver ring, your sensor, because you can have a much smaller one if you're trying to sense a smaller target. Doesn't need to be as big. They may be able to get some increased accuracy. Most likely, the bigger you are, the more sensors, the more spots you have to sense. Maybe you can get some more accuracy. I'm not sure. And I know we were talking about the differential earlier, but here's a differential from a Model S Plaid. And this has got to be from the front motor, because the rear has a motor that drives each. But here, it can show you the difference in size. And each one of these, right here, that is spinning, is connected essentially to an output shaft to a wheel. So imagine you're driving your vehicle down an icy road and you transition from ice to dry pavement, and you have a huge shock load of, a tire grabbing. This differential has to handle that shock, particularly when you have one wheel spinning at a different speed and then they both grip or grab, or all of the torque when you're accelerating is essentially being applied through this pin, these two gears, and moving the whole vehicle forward. And so you can get this huge reduction in size and weight if you have it at the motor instead of at the output shaft.
Exactly.
Let's go look at the laminates for the stator, because this was pretty cool. Can you explain how many they have and what they're used for?
Yeah, so this is the stator assembly, so we're missing about half of it that we've taken off. There was roughly 462 laminates, I believe, making up the overall stack itself. They have 4 discrete laminate styles they use, so we have some various ones laid out here. And they're doing something pretty novel with their cooling strategy for this. So similar to Tesla, which we can speak to in a second, they're actually routing oil through the laminate stack to cool the conductor ends. So if we turn it here, you can see this little hole here. Basically, it creates a nozzle for the oil to spray out onto these conductor ends to cool it. This is one of the areas of the stator that gets pretty hot, and you need to maintain this at a proper operating temperature. The laminates themselves, if we want to look at how they create that nozzle, basically the various laminate styles come together, and at the very outmost laminate, they stack one another on top of each other to create a tiny little orifice for that oil.
And then it also creates a channel. So as you see the different shapes and sizes, as they're stacked up, you can see they form a channel where the oil will actually flow through and get down very low in between these, what are they, conductor bars?
Yeah.
Right? Yeah.
We can bring over a Tesla. So Tesla does a similar approach of routing oil through their laminate stack, but in comparison to how the Tesla does it versus how Lucid's doing it, you can just see how much closer that they're bringing their oil actually to the conductors themselves as opposed to being far out on the outside.
Yeah, and this shows you a comparison of how much copper is being used. This is a 800 volt architecture, right?
Yep.
So you have a stack of 1, 2, 3, 4, 5, 6, 7, 8 hairpins right here. The Tesla motors use a wire wound method, which you get a lot of inefficiencies in your fill factor. It's incredible that this small motor with this small amount of fill factor in copper is able to produce so much power.
Exactly.
And that's something that's really kind of blown us away with the Lucid is its efficiency. And also how this stator is manufactured with the, what is it called, a continuous wire wound?
Continuous wave winding, yeah.
Continuous wave winding. Explain what that means.
So yeah, we're typically used to seeing a lot of hairpin or coil wound stators like we see on the Ford products we've examined as well as the Tesla products. And maybe we can walk over here and show some of those.
Yeah. This is a perfect example of the difference.
Yeah, so typically with a hairpin, you would have on one end
Look like that.
hairpins would be preformed to look similar to this, but on the opposing end, you would have all these ends that need to be welded together to meet all the conductors to one another. So you're looking at hundreds of welds that need to take place on the end of a hairpin stator, as opposed to if you look at this, both ends are just folded over. So this with the continuous wave winding technology, they actually just continually create the conductors in a large mat folded over on one another. And if you actually followed this, you'd see that this is just one giant circle. And so what you get with that is the high slot fill like a hairpin, but you eliminate so much of the welding operation. So in total, this thing had 24 welds as opposed to 200 welds.
Yeah, and you can see right here where they're welding to, right?
Yeah.
Now, I don't know exactly where these went, but you have 1, 2, 3, so you have your 3 phases, which will connect to probably 6 each, right? If there's 24, I don't know. They double some up, I think, don't they? Yeah. And this is quite impressive from a manufacturing perspective because every time you weld here, any inconsistency in a weld from weld to weld, you can build up some variance in the resistance and the amount of copper in that path. So by eliminating all these, you can more carefully control your welds here and even spend a little more time and effort honing this process so that you can get your peak operating performance.
Yeah, and each one of these hairpins needs to be discreetly manufactured, bent, and then they need to insert them, rebend them, clean the surface. There's a lot of steps that go into getting those welds accurate.
Yeah. And we did a whole cost analysis on this motor, which
yeah, we did.
We're going to sell. It's actually for sale now.
It is, yep.
So all of these manufacturing steps are captured.
Yep.
And you worked on that, right?
I did, yep.
Yeah. And so we not only captured the manufacturing steps, we put a cost to everything.
Yeah.
So something that's really interesting, we'll have a cost per kilowatt of power.
Yeah.
And I think this thing is probably the best.
It's pretty dense.
It's pretty dense, yeah. So that was essentially the basic layout. You got a rotor in the center with a little baby differential in the middle, going out equal lengths to two planetary sets for your gear reduction. That gear reduction is what, 7 to 1?
7 to 1, yep.
And let's see, what else? So there was this large plastic oil reservoir. It also holds the pump and the filter. So serviceable filter. So this is something that we see the Tesla going to in their 4th gen drive unit, where they're going to go to an insert filter, but it won't be serviceable without splitting the case. This still has some serviceable nature where you could come in here and remove these 3 screws to get to it. Lightweight, I like the fact that it's integrated. They're not using the spin-on, was what you see on the earlier Teslas. And then the pump, very similar to what we see on the Lightning, the Rivian, I think the Hummer, and the Tesla products.
Yep.
Where you have a low voltage pump that's going to circulate your gear oil fluid. This is important that it's not mechanically attached to the gear train, because so for an internal combustion engine, your oil pump is part, it's connected to the rotation of the actual engine. So if you have start-stop technology and you shut your engine off, your oil system stops pumping. Yeah. This is important where you can circulate that fluid from a thermal perspective, and you have this plate heat exchanger which interfaces with the glycol. Yep. So if you have a high heat soak environment, maybe you just were driving really fast and you pull up and stop, your motor stops, you can still be running this at full speed to circulate that and interface with the glycol to get it cool. Yeah. So that's important. It's a relatively expensive part of an electric drive system, and how the pump works is almost identical to what you would see in an oil pump in an internal combustion engine vehicle. It's just ran by a little electric motor. So, and what else do we have here? Man, it's so small. Look how small this thing is. And lastly, these ring gears are what the planetary set will react to. So as that differential, which we showed earlier, will spin the sun. And if these planet gears don't have anything to react to, your carrier won't move. So essentially, once your ring gear is, I'll probably just do it. So close. There. So this will be fixed. So hold this, Walker. As I spin this is the speed of your wheel. So essentially, your tire is attached to the carrier on the other side. And that's essentially how you get your 7-to-1 gear ratio. Now notice the ball bearing. This is a question we get all the time. We'll do paid calls, and people will assume that an electric motor has very few or one moving part. Guess how many moving parts this has? I asked Walker to count before we got here. Just tell him.
Yeah, we had about like 360 relative moving parts. So not even including all the component, like treating the rotor as one moving part, essentially made up of 400 laminates. But relative moving parts, we have 360 when we count them all.
And this is how we get there. So this right here, we count as one moving part. The shaft that runs the sun. Each of the ball bearings roll relative to everything else separately, and the cage itself is separate from the balls. Each planet spins separate from everything else, and then all of the roller bearings and the cage for the roller bearing are separate parts. So when we count all that up, we get 111 moving parts just in each differential, or not differential, each planetary set. Then the differential has probably another dozen or so parts, plus the bearings in the differential, which typically are not moving relative to the motor unless you're turning. Yeah. So that whole assembly is usually moving in concert with the rotor if you're just driving straight, and it only moves when you turn, but we're still counting every moving part relative to each other. So it's an incredible amount. And for other OEMs, you have a similar number, probably a little less. If you don't have a planetary set, it's much less. You're essentially counting the balls in the ball bearing and the carriers. That's where you're going to get the most of your separate moving parts. But when comparing that to an internal combustion engine, you have that many pieces in just the timing chain alone, typically. If you have a long timing chain on a high feature V6, probably has like a couple hundred links there. And then your valve train with tappets and lifters and valve springs, you easily get to 200, 300, 400 very quickly. Yeah. So this is our quick overview of the Lucid Air rear drive unit. Walker, thanks for running through all of these. Once again, this is our bread and butter. This is what we do. We analyze some of the leading technology for EVs for our customers. But we're also able to bring it to you on Munro Live to let you get some insight into what we're doing. Hopefully you got some value from this, and hopefully brought a little bit more detail or depth or our Munro flair compared to what Lucid put out in their little video. And thanks for watching, and if you could subscribe, that'd be great. We also have a brand new Munro Live podcast, which Eric has worked really diligent on. We've released 2 or 3 videos. We have a sit-down interview with the CEO of Polestar. We had Jason from Engineering Explained. We have 4 or 5 episodes coming very soon, but we'd like to get that up to maybe 10 to 50,000 subscribers, but long-form content, really good audio quality, and you can also find those episodes on your favorite podcast download place like Spotify or Apple Podcasts and wherever you digest that type of stuff. So thanks again, and have a nice day.